Hey folks, I hope that you were able to take a look at that clip from Little Big League. Really fun in class when you can introduce a problem via a movie clip, especially one that features the Minnesota Twins. So when I show that clip, not only do I pose the question of, um, Joe and Sam and painting the house, I think we can add a lot more just because of the way the movie presents it. We have a few guys who are just making guesses as to how long it would take to paint the house, and then we have one gentleman come in and state a formula and then give a correct answer. Well, we're going to find out that it's a correct answer. So the question that I pose is, first off, uh, is he right? Is the answer 1 and 7/8 the correct answer? And then secondly, is his formula correct? Where did that come from? So it's a fun ways to pose the problem. And I've got it right here on my screen. Let me slide that down. Oops. And the first thing that we do is take a look and see if we can understand the problem, right? So we've got Joe can paint a house in 5 hours, Sam could paint the same house in 3 hours. How long would it take them to paint the house together? And I usually give my students a little bit of time to discuss to make sure they really understand the question. And I think because of the way the movie presents it, it works out pretty well for them to understand the problem, because we have a few answers here that are impossible. And so the first thing that I'm going to do is I'm going to think about what's the question asking. So my answer needs to be a time, a length of time, and what am I expecting? Well, if Sam can paint the house by himself in 3 hours, I know if he gets some help from Joe, even if Joe is slower than him, that it's going to take less than 3 hours. So right there, we can disregard every answer except for that last one from the movie clip. So understanding the question, I know I've got two guys working together. I know it's got to take them less than 3 hours. My answer needs to be in hours. Now, one of the reasons that I picked this problem to do in the video, because I think it's pretty easy to present a lot of the things that we're talking about in problem solving, some of our strategies. And even though this is a simple problem, it's not an extremely difficult one. I do think this is a problem not only can be presented to younger students, maybe ninth graders, but I use it in college algebra. It's kind of surprising how much this problem can throw students from a loop, even if they're a junior or a senior. So let's see here. Let's get after this problem now. How am I going to figure this out? Doing a little brainstorming here. The first thing that I would ask myself is, what if they could paint at the same rate? Can I use a simpler example and think about what would happen with that? So let's change these numbers here for a second to Joe painting the house in 4 hours and Sam also being able to paint the same house in 4 hours. Okay, now when I do this in class and we talk about this strategy, they're pretty quick to say, hey, they're going to paint it in 2 hours. And I say, why? How do we know if Joe can paint it in 4 hours and Sam can paint it in 4 hours that they would be able to do it in 2 hours together? Well, I add them up and divide by 2. You get some really strange responses here. So we talk about, can we sketch this out? Okay. And to help sketch this out, I'm not going to draw a full picture of a house. I'll just draw a big rectangle here. And we can say, all right, well, if Joe can paint the house in 4 hours and Sam can paint it in 4 hours, let's split this up into fourths. Okay? So after 1 hour, Joe has painted 1/4. Sam has painted 1/4 of the house. And we say, okay, how much do we have left? Well, we've painted half the house. We have half the house left. So after a second hour, Joe has painted another 1/4. Sam has painted another 1/4. And the house is painted. And it's painted in 2 hours. All right, so there's our simpler example to get us thinking about it and getting us really visually into the problem. Okay, now let's switch it back to the original numbers. And since I picked easier numbers to start with here, it's going to help me kind of work here through what's happening. So Joe can paint the house in 5 hours. When he could paint it in 4 hours, we drew up that he painted a fourth of the house. Now he's going to paint a fifth of the house in the hour. So let's pretend that's a fifth. I'm not being too accurate there. But after 1 hour, he's painted a fifth of the house. Now Sam, let's say he starts on this side, can paint a house in 3 hours. So that means in 1 hour, he's painted a third of the house. Let's pretend that's a third. Okay, so let's think about this. After 1 hour, Joe's painted a fifth of the house. Sam's painted a third of the house. After the second hour, Joe's now painted 2/5 of the house, and Sam has painted another third. Now, I'm not doing a real accurate job here of sketching this, but I notice that's at 2/5 for Joe, and Sam would be at a total of 2/3. And what I notice here is 2/5 and 2/3 is more than the house, so we're actually overlapping. Which we don't want to do in this problem, right? We don't need to paint the same one portion of the house more than once. So now I've worked it down and I've said, okay, now we know that it's going to take less than 2 hours. And I think that makes sense, right? If Sam can paint it in 3 hours, Joe can paint it in 5, I think less than 2 would be a reasonable answer, and we see that here. But let's back up here a little bit. Okay. Let's see here. Oh, lots of undo buttons. All right, so after 1 hour, that's 1/5 and 1/3, and then it was after 2 hours, it was 2/5 and 2/3 here. But now I'm starting to notice here a pattern. When I did it in fourths, and now when I'm doing it in fifth and a third, I can ask myself, okay, how much do they get painted together in an hour? 1/5 plus 1/3 per hour. So I think I have a strategy. I think I have a plan that I'm ready to put in action here. I think if I can figure out their hourly rate together, I should be able to write an equation that I can solve for the times. So if I take 1/5 plus 1/3 and I get a common denominator of 15 here, let's see here, that's 5/15. This would be 3/15. Okay, they're painting at a rate of 8/15 per hour, and that's 8/15 of a house per hour. So 8/15 of a house per hour, okay? Or 8 houses in 15 hours if I write it like that with my units. And I want to know how long will it take them to do one house. So if I work at this, I want to know how many hours. I'm going to call that T hours. If I take a rate of houses per hour and I multiply it by hours, the hours are going to cancel here. It's going to leave me houses, and I want to know when is this going to be equal to one house. Well, if I multiply by 15/8 on both sides, I get T equals 15/8 hours. I did not write that down correctly. I wrote 15/18. Oops. (15/8 hours, which is 1 7/8 hours, which is the same answer from the movie. Sorry, my writing's getting a little angled like that. I'm not used to using this quite in this setup. All right, so we have the same answer. And does that answer make sense looking back to some of the reasoning that we were doing earlier in the problem? We said it had to be less than 3 hours. Now we said it had to be less than 2 hours. And we had just that little sliver of an overlap, so it makes sense that we got an answer pretty close to 2 hours, a little bit less than that 1 7/8 hours. So now let's ask the bigger question: is this formula that this gentleman came up with correct? Okay. So he said something about A's and B's. So let's change this problem to Joe taking A hours and Sam taking B hours. Now, because I've just done this problem with numbers, it makes it quite a bit easier here, and I think I can follow that same plan that I had before and just replace our 3 and our 5 with an A and a B. So what can they do together? Okay, what rate are they working at together? Well, looking back at this, Sam could paint the house in 5 hours. He did 1/5 of a house an hour. Well, now he's doing it in 8 hours, so he's got 1/8 houses per hour. Sam, who could paint the house in 3 hours, okay, was painting at a rate of 1/3 of a house an hour. So now it's going to be 1/B houses per hour. Okay. Now let's get a common denominator here. We're going to multiply this by A over A and this by B over B. So I get B over AB plus A over AB, which is B plus A, or I'll write it as A plus B over AB houses per hour. Now that sounds pretty familiar from that movie clip. However, we're not done with that problem, and that's not what the movie clip gave as the answer. So now we're going to set it up as A plus B over A times B houses over hours times T hours, and we want to get 1 house painted. Let's cancel those out. That looks good. I'm going to multiply by the reciprocal, A times B over A plus B on both sides. And I get T equals A times B over A plus B hours, okay, which is exactly the equation, the formula that the gentleman gave in the movie clip. Okay. So, looking back, let's just test it real quick. A times B, okay, going back to our 5 and 3. 5 times 3 is 15. 5 plus 3 is 8. 15 over 8 gives us the same answer that we had before. Looking back, it's good. So that's an enjoyable problem to do. One thing that I like to do then is to extend it. I talk to my students. I don't love this formula because that requires me to memorize a formula for a very specific type of problem, which I'm unlikely to do. Because the next question that I'm going to ask to extend this is, well, what if Joe can paint the house in 5 hours and together they paint the house in an hour and a half? How long would it take Sam to paint the house by himself? So we start to switch it up, and then that formula is not any good. So lots of good extensions here on switching up the provided information and solving for a rate or a time depending on those. So thanks for tuning in. I hope you enjoyed the problem.